Use the quotient remainder theorem with divisor equal to 3 to prove that the square of any integer has the form 3k or 3k plus 1 for some integer k. Here's the quotient remainder theorem. Given any integer n and positive integer d, there exists unique integers q and r such that n equals d times q plus r, and 0 is less than or equal to r, which is less than d. Now, in this case, the divisor is equal to 3. So in our proof, we're going to assume that n is an integer. According to the quotient remainder theorem, this means that n equals 3q plus r for some integers q and r, where 0 is less than or equal to r, which is less than my divisor, in this case is 3. So my remainder is an integer that's greater than or equal to 0 and less than 3. That means my remainder can either be 0, 1, or 2. So this means that n equals 3q, or n equals 3q plus 1, or n equals 3q plus 2. So at this point, we have 3 cases. In case 1, we assume that n equals 3q. In case 2, we're going to assume that n equals 3q plus 1. And in case 3, we're going to assume n equals 3q plus 2. Now the goal is to show that the square of this integer n has the form 3k or 3k plus 1. So let's take the square of both sides. By algebra, n squared equals, now 3q all squared would be 9q squared. But the goal is to show that the form of this integer is either 3 times an integer or 3 times an integer plus 1. But since this whole number has a factor of 9, we can pull out a factor of 3 and write this as 3 times 3q squared. Next, we could say since integers are closed under multiplication, then 3q squared is equal to k for some integer k. So then that means that the square of my integer n is of the form 3 times k for some integer k. So that's case 1. For case 2 and case 3, we're going to apply the same trick. We're going to square both sides. So here the algebra is that n squared equals, now if we square 3q plus 1, we're going to have to FOIL that into 9q squared plus 6q plus 1. Now since the first and second term are both divisible by 3, we can pull out a factor of 3 from those first two terms to write this as 3 times some integer here, and then plus 1. And so in this case, 3q squared plus 2q would be my integer k, and we would be done. I would formalize this a little bit more, but you can use case 1 as an example for our framework. For case 3, we could square both sides and get n squared. If we FOIL out 3q plus 2 all squared, we would get 9q squared plus 12q plus 4. Now, if you notice here, this 4 is not the remainder that we want. We either want a remainder of 0 or we want a remainder of 1. So what we can do is we can rewrite this 4 as a plus 3 plus 1. And now we can factor out a 3 from all the other terms and write this as 3 times 3q squared plus 4q plus 1, and then plus 1. And so in this case, my integer k would be 3q squared plus 4q plus 1, so that this is 3k plus 1. And to finish off case 2, this would be 3k plus 1. And so you can see that regardless of what the remainder is, by using the quotient remainder theorem, we can prove that if we square any number, we get a number of the form 3k or 3k plus 1. We never get a number of the form 3k plus 2, which is kind of interesting. That means if you square any number, and then you divide that number by 3, you're never going to get a remainder of 2.
For part B, we have to use the mod notation to rewrite the result of part A. So since the square of any integer has the form of 3k or 3k plus 1, that means any integer mod 3 is either a remainder of 0 or a remainder of 1. The result of mod is the corresponding remainder. So either remainder is 0 or the remainder is 1. Notationally, we would write this as n squared mod 3 is either 0 or 1. And that's the answer to part B. Thanks, everyone, and I'll see you in the next video.